Section 10.2 is on page 689, talks about calculus with parametric curves. I went back to 10.1 and stole the original definition. X is a function of t and y is a function of t. If I would like to take y, which is normally my f of x, and I would say, well, y is actually f of t, and this is f of, and x is g of t. And if I want to take a derivative, if I take a derivative of this, I will get f prime of t equaling the derivative by that chain rule times g prime of t. So if I solve for f prime of g of t, that would be f prime of t divided by g prime of t. And this is f prime g of t is actually my x, which is initially what I wanted. So pretty much I just found a way of finding a derivative in parametric equations by bypassing all of this and saying, if you want to find dy dx, which is what this equals, then simply take f prime of x dy dt over g prime of x, which is dx dt. And there it is. So this is one way of applying this quickly. I don't like that x. Here we go. Now, I'm going to show you another way of doing this, and that's mainly for 5c. I could say also, so I'm not big on the derivation, but I'm big on the application, something you need to do in 5c. If y equal f of t and t equal g of x, then dy dt by the chain rule is dy dx. Man, come on, I gotta slow down. Dy dx, dy depends on t and t depend on x. I could say, I'm gonna put this on one line, I could say dy dt times the reciprocal, right? If this is a multiplication, can't I say I'm gonna divide by the reciprocal? And isn't that saying dy dt divided by dx dt? And there it is again. So this is something that you did in 5a a bit, but I don't know how much you got out of that when you did applications, but in 5c that's a massive deal. And the second derivative I provide on that formula sheet that I gave you. If you want to find what the second derivative is, the second derivative with respect to x is the derivative with respect to x of dy dx, and that turns out to be d dt of dy dx dx dt. Keep in mind, this is already right there. And we're going to practice this. That's not a big deal. Something comes up. So this is provided on your test. You just have to kind of tweak it a bit, get used to it, and we know what a second derivative is used for, right? Yep, concavity. That's right. Now, there is one more thing I want to mention. Given dy dx, y depends on t, and x depends on t. That's really simple. If I ask for where would the curve, where the curve has a horizontal asymptote, tangent, I'm not getting anything right today, horizontal tangent, and the curve possess or has a vertical tangent. So let's see. We have a tangent line when the slope of the line is 0, and a slope of a line is 0 if in this case, the top equals 0. And we have a vertical line if the slope of the line is undefined. Since this is the slope of the line, that's when dx dt equals 0. And that's something that you need to keep in mind as you do these problems. And here we are. Alright, good. Now, let's look at some problems. I'd like to start off with the following two problems. First problem just says find dy dx, so something to get used to. It's not that challenging. Well, think about it this way. Y depend on t, and x depend on t. There it is. What's dy dt? That is 1 plus the cosine of t. And what is dx dt? Product rule. And there it is. Nothing more than a derivative. And what do we use derivative for? The traditional. Find an equation of the tangent line to the curve at the point 0. Well, let me get if t equals 0. If I put 0 in there, sine of 0 is 0. E to the 0 is 1. So my equation is y minus y1 equal m into x minus x1. I'm almost done. All what I need is the slope of the line. And what's the slope of the line? That's dy dx. Well, that is dy dt. You don't need to write that down just until we get the hang of this. And again, you got to keep in mind you're going to take derivative of y first, and then x, the product rule, e to the t times the sine of pi t, plus pi times e to the t cosine of pi t, evaluated at t equals 0. What do I get? 2 over, that's a 1, that's a 0, and that will be a pi. There it is, done. Not much to do really. Once you get acquainted with this, but the application of this are enormous, and we're going to use it heavily later on in your next problem I'd like to look at is the following. 11 through 16, find the first derivative and the second derivative. Well, let's do the first derivative. dy dx is dy dt over dx dt. That piece is done. Find the second derivative. That is d dt of what I got over dx dt. That is, so d dt of 2t minus 1 over 3t squared over dx dt. If you didn't manipulate this, if you didn't simplify at all, then it's right there. And if I want to take the derivative of this, I could split that up. You know, I could say that's 2t over 3t squared, but it doesn't really matter. That's going to be derivative of the top times the bottom, minus the top times derivative of the denominator, all over the denominator squared, and that in turn becomes 6t squared minus 12t squared plus 6t all over 3t squared cubed. That would be negative 6t squared plus 6t divided by 3t squared cubed. I know that simplifies a bit. I could factor a negative 6t out of the top. That would be t minus 1. And in the denominator, that's 27t to the 6. I know this reduces by 3. And there it is. Now, if I want to know where the curve is concaving up or down, I'm going to take where does the second derivative equal 0, or where does the second derivative not exist. And the second derivative equals 0, that's when we get negative t into t minus 1 equals 0. That's t equals 0 or 1. So I have those test points. And the denominator, 9t squared equals 0. That's when t equals 0. Well, I'm getting the same point still. That's not bad. This is 0. This is 1. I'm going to pick my test points, a point to the left of 0. If I pick, let's say, negative 1, and I'm testing negative 2t times t minus 1 over 9t to the 6. I notice the denominator is always positive. For the top, negative 2 times negative 1 times negative 2. 3 negatives will yield a negative. A point between 0 and 1, say a half. Negative 2, a half is positive. 1 half minus 1 is negative. That will be a positive. And a point to the right of 1, negative 2 times a positive 1 times 1, that will be positive, or 2. So this will be concaving down, concaving up, and concaving up. And here they're only asking about where is the graph concaving up. And you would say the curve, oh boy, is concaving up from 0 to 1 union with 1 to infinity. And there it is. I'm going to do a few more problems.